Okay. A wheel starts from rest and rotate with constant angular acceleration to reach angular speed of 12 radians per second in 3 seconds. Find the magnitude of angular acceleration of the wheel and the angle in radians through which it rotates in time interval. This is an example from survey. University physics for science and engineering, which is usually a standard textbook for most of the physics students. Well, not physics students who learn physics worldwide. Okay. So what this question given us? It gave us that it start from rest. Well, that means omega 0 is 0, start from rest, and rotate until the angular speed is 12 radians per second. This is final angular speed. In 3 seconds, it gave the time interval. So we can calculate the magnitude of angular acceleration and the theta or the angles to which it rotates by using the formula and definition. So what we know from the equation is that omega 0 is 0 radian per second because it starts from rest. Omega is 12 radian per second, and then times is 3 seconds. By definition, the angular acceleration is well, 1 minute, please. By definition, the angular acceleration is the change in angular speed versus time. So the change in angular speed is the angular speed final minus angular speed initial divided by the time take. So we have the final angular speed of 12 radians per second and initial angular speed of 0. And this happens in the interval of 3 seconds. So what we get is the alpha or average alpha is 4 radians per second squared. And that's the change in the acceleration of the system. Now you can doing another things is that theta is omega plus omega 0 over 2 times the time. Or you can use the formula theta is omega 0 t plus 1/2 alpha t squared. Well, initial is 0, so you got theta is 1/2 of 4 times 3 squared, or it is 18 radians. Or you can use theta equal to omega 0 plus omega over 2 times t. And add them up, it is 12 over 2 is 6 times 3 is 3 seconds. So 6 times 3 is 18. So it's still 18 radians. Correct answer. So the question is how many radians it takes. So it is 18 radians. But how many rounds? You can say that one round is 2 pi radian. So 18 radians is 18 over 2 pi rounds, or it's roughly 2.86 rounds. So it's just 2 rounds of rotation to get to the final angular velocity, angular speed. So today we will start a next step in understanding the rotation mechanics. Okay. Well, we have the acceleration, the speed, and the distance. So we are going to talk about force. After all, Newton's law always true, whether you talking about motion in linear motion or angular motion. So there must be a force that causing the object to rotate. Okay. So suppose we have an object that tied up to a fixed point. It means that this object cannot move further away from that fixed point than the distance r. Okay. So the only motion that it can appear here is along the circular motion. Now, if you're pulling the object with the force F, making angle theta to the radial acceleration, to the radial or position vector, we'll see that there are two forces that can break out of this. One is F cosine theta point outward in radial direction. And the other one is perpendicular direction, F sine theta. And of course, because the object have to stay on the dot track. So F cosine theta will be counterbalanced with the tension in the string. So anyway, the radial axis force is going to cancel out. So the only force that you have left on the object to move is F sine theta. And that is perpendicular to the radial or tangential to the curvature of motion. So this is the force that caused the object to move. Now, if we apply just a simple Newton's law, summation F equal to ma, and our F is F sine theta is m times at. At is the tangential acceleration. But we also know that at can be written in terms of angular acceleration by r times alpha, and alpha is the angular acceleration of the object. So we can just put in the magnitude F sine theta equal to mr alpha instead of mat. Now, the thing is, it's not only F that caused the object to move. So you have F sine theta. If you use this force closer and closer to origin, you will see that the rotation of effect on the object will be smaller. But then eventually, if your F sine theta is appear on the center itself, the fixed point itself, it will not cause any motion on the object. So not only the force that are important to the motion of, to the rotation of the object, where that force is applied is also important. So if I'm doing this by multiply with radius one more time, I got Rf sine theta equal to mr square alpha. Now this is involved the radius. So, okay, just a moment. Just a moment. Let's get back to our business. So not only the force that are important to the motion, the point where that force is applied is also important. So if it applies at R, you got R times F sine theta equal to mr square alpha. And then we define this as torque, okay? Using the symbol torque is a T in letter Greek, and it's defined as R times F sine theta, or that vector of torque is R cross F. It is a force that causes the object to rotate or twist. So for one simple point, R cross F torque is mr square alpha. This is one dot over the light rod. Now, if you have many systems that coming together, for example, you have 2, 3 dots. You got the force on, you have the Newton's law, okay, for each of them. So if the object are more than 3, so suppose they have 10 times to the 23rd object stuck together, we have this object called rigid bodies, okay? And the rigid bodies is the bodies that the mass is coming in together, and it remains its shape when you apply force on it. So they don't change shape according to rotation. And we define the moment of inertia as the summation of mi/ri square. Mi is the mass of the object, number I, and ri is the distance to the axis of rotation of that mass. So each of the object will have this moment of inertia. And now we have Rf sine theta equal to mr square alpha. We can write it down as torque equal to I alpha. This is Newton's law for rotation. Okay, it is equivalent to F equal to ma, but F equal to ma is used in linear motion, but torque equal to I alpha is used in rotation. Here are some values of the moment of inertia. Okay, it's a properties that show how much torque you need to cause an object to spin. Or this is actually the initial part of the equation of Newton's law. Now each shape have different value for moment of inertia. For example, if you have a hollow cylinder, we have a cylinder, but the center is empty. The moment of inertia is equal to mr squared. Now, if you have a solid cylinder, you put some things in the middle to its full. It's turned into a solid cylinder. Now the solid cylinder, the moment of inertia is 1/2 mr squared. Then the third one is the hollow sphere. Okay. The hollow sphere is, for example, a football. The moment of inertia of the football is 2/3 mr squared. But if you have a solid sphere, like a wrecking ball or some things that have a round in shape, but completely filled, it have the moment of inertia of 25 mr squared. And a hoop, which is one form of a hollow cylinder, is also having the moment of inertia of mr squared. So let's take a look at this example. Okay. Let's leave you read this question for about 1 minute. Well, this example, a solid cylinder of mass 1 kilogram and the radius of 0.1 meters can spin without friction around its axis. So it can spin around. A string is wrapped around the cylinder. So you put the string on the cylinders and then wrap around the cylinder. Well, how many rounds? We don't know. But then you pull it out with the force of 5 newtons. So the question asks, what is the angular acceleration of the cylinders? And then find the angular velocity and angular displacement after 2 seconds. Now what happened is that once the string is completely out of the cylinder will start to slow down. Okay, but as long as your string is pulling it, it have some torque, so it will continue to speed up. So let's take a look at this problem. What they given us is the mass of the cylinder and the radius. So we should be able to find the moment of inertia. Now it's also said that it was pulled by a string with 5 newtons force. So we have the F, we have the radius, which is the radius of the cylinder. So we do have a torque on the system. And because we know torque, we know moment of inertia, we also can find the acceleration, angular acceleration of the cylinder. And afterward, assuming that is constant, you can find the angular velocity and angular displacement after the pull. So let's continue with gathering information. Well, the torque is R cross F, or half the magnitude of R times F sine theta. And in this case, when you pull an object of the cylinder by the string that wrap around it, the angle between the force and the radius is 90 degrees. So we have torque equal to Rf sine 90, and the radius is 0.1 and F is 5 newtons. So torque is 0.5 Newton meters. That's the unit of torque. What? Now, I think I missed one spot. Okay. The moment of inertia of the object because it is a solid cylinder, it has a moment of inertia of 1/2 mr squared. So plug in the mass of 1 kilograms and the radius is 0.1 meters. And you have the moment of inertia of 0.5 times 10 to the minus 2 kilogram meter square. Okay, or 5 times 10 to the minus 3 kilograms meter square. So from torque equal to I alpha, torque is 0.5 Newton meters. Moment of inertia is 5 times 10 to the minus 3. So our acceleration is 0.1 times 10 to the 3 or 100 radians per second square. Now, there's part B, they ask what is the angular velocity and angular distance if t equal to 2 seconds. We are assuming that it starts from rest, omega 0 is 0. So you got omega equal to omega 0 plus alpha t, and then you can plug in the value for alpha, which is 100 radians per second square, to the time, which is 2 seconds. So after 2 seconds, the angular speed of the object will be 200 radians per second, and the acceleration and the distance travel will be 1/2 of alpha t squared. And you put in alpha equal to 100. So it is 1/2 of 100 times 2 squared. And in this case, we have 200 radians. Okay. Let's see another example. A wheel of radius r and moment of inertia I was wrapped with a string, and at the one end of the string connect to the mass m. If we release the mass, find the acceleration of m and find alpha. Now let me explain this. You have a wheel, or it is a form of a cylinder, and then wrap up with the string, and the other end is connect to mass small m. And when released, okay, what happened is that the mass small m will be attracted to the Earth with the acceleration of g, and it has a force of mg, Now it pulling the string, so the string pull back, and in the meantime, the string is going to pull on the wheel of the radius r. So what happened is that the wheel will start turning, and the mass m is going down with acceleration that is not equal to 9.8 meters per second because of the tension in the string helps. So you can start up with equation for the small mass m. It's according to Newton's law, mg minus t equal to ma. Okay, and mg that is the first equation. Now the second equation is that if we're talking about torque is move on to the wheel. It have reverse pull by tension T, and then it have the radius of R. So we have torque equal to T times R. And because alpha is the angular acceleration, can be written as A over R. Okay. So we got tension is torque over R, and torque equal to I alpha. And alpha is A over R. So we got that the tension is IA over R squared. A is the acceleration. So we can plug this back into force equation. Mg minus T equal to Ma. But we can find that T is IA over R squared. So we have Mg equal minus IA over R squared equal to Ma. And then rearrange the term, we got the acceleration is G divided by 1 plus I over mr squared. So the effect of the moment of inertia on the wheel is making the object small m fall with lower angular velocity, lower acceleration. Okay. So for solid wheel, I equal to 1/2 mr squared. So A equal to G divided by 1 plus I over mr squared. And you see that you substitute I is 1/2 mr squared, and you cancel it out with mr squared. So it's this, notice capital M and smaller m R and R cancel. So what you have is that acceleration is G divided by 1 plus capital letter M over 2m. So it depends on the mass of the wheels and the mass of the object. Okay. So this is the summation page. For linear motion, you have equation V equal to U plus AT, S equal to UT plus 1/2 AT square, and V square equal to U square plus 2AS. And we have the same lookalike formula for angular motion. Omega is equal to omega 0 plus alpha t, and theta equal to omega 0 t plus 1/2 alpha t square, and omega square equal to omega 0 plus 2 alpha theta. Now we have the Newton's law for linear motion is summation F equal to ma. For rotation is summation torque equal to I alpha. And the force can be written as the change in momentum. And in rotation, we can define the Newton's law of rotation by torque equal to I alpha. And then by definition, torque is R cross F. So it has a unit of a magnitude of IF sine beta. Beta is the angle between L and F. So we have one term extra on the linear side, which is the momentum. So in angular motion, we define angular momentum as the a result when you have the force on an object. So by the same definition, the torque is equal to the rate of change in angular momentum. So I do some proof here. Torque is I alpha, and it is alpha is d omega by dt. So torque is I omega d by dt of I omega, and this is called angular momentum L. And if we looking at another term, torque is R cross F, is torque net, which is the net force on the object. So we get R cross MA. t, or r cross m dv by dt, and you get torque equal to m r cross dv by dt. Okay. We're playing with math here. D by dt of r cross v, you have two terms according to derivative y part. dr by dt cross and v, and then plus r cross dv by dt, which is the result that we need. Okay, so the first term v cross v is 0. And then we have r cross m dv by dt equal to d by dt of r cross f. Okay, so we have torque equal to d by dt of r cross v. So we have m r cross v of this is L. So we have angular momentum not only equal to IR omega, it's also equal to F equal to R cross MV, or R cross momentum also. So we compare this to a linear momentum. Force is dp by dt. If force equal to 0, the momentum is constant. Without external force, an object will conserve their momentum. So it have p times equal to m times v is constant. Now the same things goes with the angular motion. By definition, torque is the rate of change of angular momentum. And without any external torque, the angular momentum of the object is constant. Okay. So when this constant, it depends on the mass of the object. If the mass is increased, so we have the initial moment of inertia increase, so the omega will decrease. And if I decrease, omega will increase. So that's the problem of conservation of momentum. We just finished Winter Olympics. One application of angular momentum is when figure skating spin in her feet. Okay. When they spin, usually they start with extended hand. And then that point, the spin usually low because it have high angular momentum, high moment of inertia. Now, once he pull his hand back in, his moment of inertia is released, but then it's lower. In order to compensate, to keep the angular momentum constant, the lower the moment of inertia, the higher the speed. So we can use the angular conservation of angular momentum also as the conservation of momentum. Okay. Let's take a 5 minutes break. Okay, and I'll come back within 5 minutes. Okay, let's continue. Somehow today I was too tired, more than usual. After 3 hours of speaking, okay, maybe after this class I will take some naps. Let's talking about conservation of angular momentum. Review it again. Well, when you watch figure skating, you see that when they moving on the ice, and then there is a show that he's spinning around. When he did that, there are no external torque applied on his body. So at first, if he extend his hand further away from his axis of rotation, his moment of inertia is increased. So his moment of inertia is large. So as a result, to conserve the angular momentum, his body will rotate at slower speed. Now, if he pull his hand toward himself, his moment of inertia is going to be decreasing, and to conserve the angular momentum, his speed of rotation will speed up. Okay, if you watch a rerun of the Winter Olympics, you will see this in figure skating. And this is called conservation of angular momentum. I will give you an example that a little bigger, which is the white dwarf stars. A white dwarf star is the final stage of stellar evolution. So it's actually the corpse or the ending of most of the normal stars that are not bigger, much bigger than the sun. Well, when it's the stars end their life, at the end of their life, the star collapses into itself. So the mass is going to compress into a small object that is not bigger than Earth, but it has the mass of the whole stars. And in doing so, initially when it is a star of larger radius, their moment of inertia is large. So the stars is slowly turning because they have to conserve their angular momentum. But when it's collapsed, the radius of the stars is increasing dramatically. Okay. And as a result, to conserve the angular momentum, we will see that it will speed up into a milliseconds rotation period. Okay. So if originally the star have the momentum inertia of 2/5 mr squared, this is the momentum inertia of the solid sphere. And then after its collapse, it has the momentum inertia of 2/2 m2r2 squared, 2/5. So we have that the momentum inertia original and the momentum inertia final is m1r1 squared divided by m2r2 squared. And usually when it has that problem, we'll see that when the star collapse, it lost some mass, but the mass of the M1 usually 10 times that of M2. But the radius of 2 is 1,000 times smaller than the radius of M1. So we plug those in, I will see that the moment of inertia of the object of the white dwarf compared to when it was a star is 10 to the minus 7. Now, because momentum inertia decreased by 10 million times, the speed or the angular velocity of the object will increase at the same rate. So we using the conservation of momentum I1 omega 1 equal to I2 omega 2, and I1 omega 1 is 2 pi over period y over T1 equal to 1/2 2 pi over T2, and we see that T2 over T1 is I2 over I1, and that is approximately 10 to the minus 7. So the white dwarf, the stars will speed up, okay, their speed by 10 to the 10 million times. So let's assume that the T1 has a magnitude of 24 hours. It's a period of in normal circumstances. But if it's collapsed down into a white dwarf, T2 is 10 to the minus 7 T1, and is roughly around 8 milliseconds. Okay, that is the white dwarf rotation period. Okay. So let's check. We have only a few pages left. The next topic is rotation energy and rolling motion. Okay. When we're talking about rotation, we usually means the fixed axis. So the axis is fixed, it's not moving. And we have energy of, we have the speed of rotation of omega times r. So we can think about conservation of energy for one object, which is 1/2 mv squared, and plug in v equal to omega r sin. You will see that it is the kinetic energy of a object is 1/2 mr squared omega squared. Now, if you have several objects combined, M1, M2, M3, and M4, they are all rigid bodies. This means that the distance between each of them are constant. So it's keep their own configuration. So the total kinetic energy of this object in this case is 1/2 summation of MIRI square omega square, and this is called 1/2 I omega square. This is rotational kinetic energy. Okay, so it's the energy of rotation. Now, if we're talking about rolling, rolling is a combination of linear motion and rotation. So if you look at the center of the rolling object, if you are at that center, you will see the object turning around or spinning or rotation around its axis. However, as it rolls down on the floor, the center of the object or the cylinder is also moving by the same distance as the rolling distance. So example, if it roll one round, the center of mass is going to move by a distance of 2 pi r. And the object will roll down around its axis by one laps. So the total energy when you have both rolling and translation, the energy is 1/2 mv squared plus 1/2 I omega squared for translation kinetic energy and rotation kinetic energy. So when you have an object that rolling, you remember that there are two terms of energy. One is for translation and one is for rotation. Okay, let's have a look at the problem. An object rolling up an inclined plane. So we have an inclined plane and we have some circle, some smooth object and roll it up the inclined plane. With initial velocity v, the question asks how high it can go up the plane. Okay. So we can use this conservation of energy by picking 2 points. Point 1 is at the bottom of the plane, and point 2 is at the top of the plane. Because the energy is conserved, so E1 plus must equal to E2. And at the beginning, it's only half the kinetic. So it is 1/2 mv square plus 1/2 IU square, I omega square equal to mgh. And then I plug in the V equal to omega R inside because as the center of mass is moving, it's also turning. So 1 turn of the center of mass is equal to 1 radius. So it is 1/2 m omega square R square plus I 1/2 I omega square equal to mgh. And you pull out the mr square, you got 1/2 mr square omega square times 1 plus I over mr square equal to mgh. So we have the height that it can roll up to be r square omega square over 2 g's, and then times 1 plus I over mr square. So the height of the object that goes up will depending on the moment of inertia of an object. So for hollow cylinder, it is mr square. For solid cylinder, it's 1/2 mr square. And the sphere is 2/5 mr square. And we will see that the larger one is the hollow cylinder. That means the hollow cylinder will going highest at this point. So I think I'm half an hour quicker than usual. Let's stop share for a few minutes and stop record. Our next topic is wave. And we already discussed simple harmonic motion already. So we are going to discuss another phenomenon that is the phenomenon of waves and harmonic motion. So the question is, what is waves? And if you look at the pool that have this smooth surface, and then you drop the stone inside into the pool, and then immediately you will see that the stone, after it touched the surface of the water, is create a ripple of waters that going up and down. And that ripple is going to spread out in the pool until it fills. Okay. So in a sense, the wave can be explained as a transmission of disturbance from one point to another. Okay. So it's caused the surface of the water to moving from its equilibrium position. So we call that a disturbance. And not only it's carried the disturbance from one point to another, it also carries energy because it initially the surface of the water is at rest. Suppose you have some of the floating object floating on the surface of water. At the beginning, it doesn't have any energy. Just floating there, stay still, doesn't have any kinetic energy. But once the wave arrives, you will see that the object is going up and down. So it receives some energy from the waves, and then it can transmit it to another object. So in order to get the sense of the wave, let me check at this thought experiment. If you have a set of spring and mass system that are not connected in any way, and then you set up one string to oscillate. Well, because it doesn't connect in any way, all the three strings will remain at rest. However, if you tie the small string together between the mass, and then you set one mass to oscillate again. The thing is, what you saw is that when it oscillates, the spring that attached that bodies to the next one is going to move up and down. And then it will causing the second object to oscillate also, then the third object and the fourth object. And this is the process of wave. It's the process of sending the disturbance from one point to another. So when you disturb one point to oscillate, it's transmit to the medium. So we call this the medium, okay? The medium that the wave is traveling on. So it's not only create the disturbance, it's also bring energy, and it's also bring information, because our perceptive is always depending on the process of waves. Your eyes is looking at electromagnetic waves. Your ears is listening to the sound waves, and your body can feel the vibration of the seismic wave. So it's one way to say that it is a process that we use as to communicate with each other. And I say here, wave is the basis of all communication. So let's discuss the types of waves. Well, we can categorize wave in two ways. The first way is by the way that it uses mediums or not using the medium. Usually the waves that traveling within our everyday life requires to have the medium for it to move on. And if it requires a medium to move on, we call it a mechanical waves. And you will see that several objects is being the wave itself, and is also being a medium. For example, the wave in the string and wave in water. So in water, it is also the water. Air is the sound, which is the sound wave requires to have air. Okay, and waves in solid. For example, seismic wave requires to have the medium, which is the ground and the rocks that is going through. Now, there is another type of wave that is not required to have a medium at all, and that is electromagnetic wave. Okay, and the reason the electromagnetic wave doesn't require the medium is that it consists of two vectors that are induce each other to change. And that is called the electric two components, the electric field and the magnetic field, that causing it to move, induce each other. So it's the only type of wave that have two components, have electric field and magnetic field. And it's also the only component that don't require to have the medium. It can move in vacuum. Okay. So the ratio between the electric field to the magnetic field is 3 × 10⁸ meters per second, which is the speed of light. And I will just going ahead one more topics. Another category is to separate the waves is by the mode of their vibration. So if it vibrates in the direction that is perpendicular to their propagation, propagation is the direction that the wave is moving. For example, in this case, the direction of propagation is from left to right, and the direction of oscillation of the medium is from up to down. So this is called transverse wave, because the direction of oscillation of the medium is perpendicular to the direction of motion of the wave. The perfect example for this is the wave in the spring, wave in the ropes, a surface wave of the sea, for example. This is all the transverse wave. The other waves is called a longitudinal wave. Okay, this is a longitudinal wave is a wave that the motion of the medium is in the same axis as the direction of propagation. So it's going back and forth. For example, in this case, you will see that this a dense pack of spring. Okay, this is the dense pack of spring. It's caused by the motion of the spring. And you will see that the string is moving back and forth in the left to right and right to left axis. But it's also in the same direction as the direction of propagation. So this is called longitudinal wave. And the example of longitudinal wave is the sound wave and another seismic wave that is called P-type. It is a seismic wave that are longitudinal. So here's a summary. The types of waves can be separated by using the medium. If it's used, it is a mechanical wave. If it's not used, the medium, it is electromagnetic wave. And the other way is the mode of vibration. If it's transverse, it is or perpendicular, it's called transverse wave. If it's longitudinal or the same direction, it's called longitudinal wave. So in a sense, electromagnetic wave is also a transverse wave because the motion of or the change of their vectors is perpendicular to the direction of motion of waves. Okay. Let's see some terms that are important in this matter. Suppose we have the waves, maybe water waves along the ponds. you see that it has a ridge or a crest, and on a trough, which is the lowest point, the crest is the highest point. And the distance from lowest point to lowest point or highest point to highest point of each wave is called a wavelength. So it is a distance between 2 points. It is actually the 2 points of the same displacement. Okay. It's called the wavelength or lambda. It is represents the length of one cycle of waves. So after this wavelength, it will repeat itself. So this is called lambda of wavelength. Now another term is the amplitude, which is the maximum displacement of the medium. Okay. And we also have the frequency, which is the numbers of waves that going through the observer by 1 second. Okay, and we have that as a frequency. And the inverse of this frequency is the period. Okay, so the period is the time it took for one wave to complete movement. And if we take a look at the maximum point of the wave, you see that it is pushing forward. And the speed that the wave is moving forward is called the speed of wave. So, because if the wave traveling by one wavelength, it took the time equal to the period of motion, of vibration of the medium. So we see that to travel by a wavelength, it took the time of the period to move. So we can define the speed of wave to be the wavelength divided by the period. And because the period is one over the frequency, okay, the period is the time it took for one wave to complete. So inverse of the period is the frequency or the numbers of waves that traveling to in 1 second. So we have the speed of wave equal to lambda over p or f lambda. Okay. Let's come back and take a look at the example on Tuesday. And then I hope that we can finish this chapter by next Wednesday. But as of today, I think that I'm exhausted. So I will just wrap this up a little bit sooner than usual. So see you again next Tuesday. And next Tuesday, we'll have a quiz on work done and conservation of momentum. I will see you next Tuesday. Thank you very much. Bye.